Welcome to the lecture 8 or module 2 of the course called Game Theory and Economics. Before we start this lecture, let me take you through what we have discussed in the previous lecture. We have basically introduced the idea of best response functions. This was done because in many cases the actions of the players may not be discrete and they might be continuous variables, and if they are continuous variables, there is no way in which you can construct payoff matrices and seek for Nash equilibria. So, to find out the Nash equilibria in the case where the actions of players might be continuous variables, an infinite number of actions, we need to use the idea of best response functions. And what we have seen is that if we construct the best response functions of players, then the Nash equilibria or Nash equilibrium will be situated at the intersection point of these best response functions. In particular, if we have two players and if we construct the best response functions for them, then the point at which they intersect, these best response functions intersect, will be the points of Nash equilibrium. So, that is what we have done, and we have done some exercises also for applying this idea. Today we shall do another exercise and move on to the next topic, and this is not exactly an exercise, it is an example, and this idea is the following. This is called contributing to public good. If you remember, we have already done one or two examples of public good. Public good are cases where people derive some utility from the goods, from that public good, but I cannot exclude anyone from enjoying that public good. For example, a government road maybe. I am deriving some benefit out of that government road, but I cannot exclude someone else from using that. And so, there is a problem of whether that public good will actually be constructed, because if you cannot exclude anyone from using that good, then you will not be able to make them pay also, because if I can use that good without having to pay for it, I will not pay for it. So, there is an inherent problem of provision of public good which cannot be solved from standard private good framework, and this is another example of that. And here the question is not whether people will contribute or not. So, it is not a 0-1 kind of decision. It is a decision of if people contribute, then they may like to contribute more or less also. I mean, I can choose any number between 0 and infinity denoting the amount of money that I am ready to pay for the public good. So, here the question is not 0 or 1 or contributing, not contributing, but the question is not contributing, and if contributing, then how much to contribute. So, I have infinite number of actions here. So, let me tell you the setup first. Suppose, to make the problem simple, there are two players. So, these are the players' actions, their contribution for the public good. And we shall denote this by C1, C2. What is the nature of this C1 and C2? C1, C2 can lie between 0 and infinity. It can take any non-negative value. And what are the preferences? Preference of any player is given by the utility function of that player or the payoff function of that player. So, let me denote payoff function for player I as ui. It is a function of two variables, both his contribution and the contribution by the other players. And also I assume that to begin with players have the endowment of W1 and W2, that is, this is their initial wealth which are positive, and out of this W1 and W2 they decide how much to contribute or whether to contribute at all. If they decide to contribute 0, that means they are not contributing. Okay, how does this payoff function look? This is given by Vi C1 plus C2 plus Wi minus Ci. To interpret this function a little bit, this first part, that is Vi part, if I look at it more carefully, I will see that it is a function of C1 plus C2. Now, what is C1 plus C2? C1 plus C2 is the total contribution made by two players together, put together. So, this is their total contribution for the public good C1 plus C2, and depending on the value of C1 plus C2, some amount of public good is being produced. Vi tells me what is the benefit that player I is getting out of that total amount of public good. So, in particular, if C1 plus C2 is high, then more public good will be created and Vi will be high. So, I can safely assume that Vi is an increasing function. So, Vi dashed is positive. That is a reasonable assumption to make. Another assumption that we shall need in understanding this problem of public good is that Vi double dashed is, I am assuming that this is negative. This essentially means that the Vi function will be a function like this. So, this is my Vi and this is C1 plus C2. As C1 plus C2 rises, Vi rises. So, I have positive slope of this function. At the same time, the slope goes on declining, which means that the second derivative is negative. That is what I have written here, second derivative is negative, but the function is positively sloped. Let us suppose that it starts from 0 to avoid complications. Now, question is, if this is the setup, if there are two players, each player can contribute towards the construction of public good, and that contributions are called C1 and C2, and their utility functions are given, preference or payoff functions are given by this. Then what is the equilibrium, or what are the equilibria? In particular, will there be any equilibrium where people contribute towards the public good, or can there be any equilibrium where people just do not contribute and no public good is constructed? We have seen such examples before, where there was an equilibrium where nobody was contributing towards the construction of public good. So, that is the problem here, and we want to solve this problem by using the idea of best response functions. And how to do that? We know that best response function for player 1 will be that C1, it will give me that C1 as a function of C2, which maximizes player 1's payoff. So, I have to find out that C1 as a function of C2. This is given by, also called B1 C2, that maximizes U1, because U1 is the payoff function for player 1. So, I have to maximize U1 with respect to C1, because on C1 player 1 has control, on C2 player 1 does not have any control. So, max with respect to C1, and this is the familiar problem of maximization and minimization. What we need to do is to set the first derivative with respect to C1 of this function equal to 0. That will be my first order condition, and I know what is U1. U1 is this much. So this is what? This is V1 C1 plus C2 plus W1 minus C1. This has to be equal to 0. So this is nothing but V1 dashed applying the chain rule here. Here I am applying the chain rule. And what is V1 dashed? V1 dashed is the derivative of V1 with respect to C1 plus C2. So from here what I get is V1 dashed is equal to 1. Now remember what is V1 dashed? V1 dashed, when I think about V1 and V1 dashed, V1 is a function of C1 plus C2. So V1 dashed is also a function of C1 C2. So I can as well write it as V1 dashed C1 plus C2 is equal to 1. And from this I can take the inverse of 1, V1 dash inverse of 1. So C1 is equal to V1 dashed 1 minus C2, and this is the best response function of player 1. So it expresses C1 as a function of C2. So I have C1 as a function of C2. This is my best response function. Before I go into the best response function of player 2 and try to find the equilibrium or equilibria for this problem, let us have a closer look at this one. What it essentially is saying, that if C2 changes, the change in C1 will be in the opposite direction. If C2 rises, this side, this right hand side is declining, and so that means C1 is declining, which means that if player 2 contributes more, player 1 will contribute less. So there is an inverse relationship between them. In fact, the slope is -1. So 1% rise in C2 will lead to 1% fall in C1. How do I interpret V1 dashed 1? And if C2 is greater than 0, then it is given by this. The relationship between C1 and C2 is given by equation 1. And if C2 rises so much that it becomes greater than V1 dashed 1, well, if C2 exceeds V1 dashed 1, then this equation 1 cannot give me the solution for C1, because this will tell me that this has to be negative, but C1 cannot be negative. I have this restriction before. C1 cannot be negative, it has to be positive or 0. So if C2 exceeds V1 dashed 1, what is the minimum value C1 can take? So the range of values for C1 is such that it varies from 0 to V1 dashed. The maximum value it can take is V1 dashed. That is, this value of C1 is dictated by the best response function of player 1. So which means that player 1, if he is trying to maximize his payoff, will never contribute more than V1 dashed. If the other player is not contributing at all, then player 1 will contribute V1 dashed, which means that V1 dashed is the worth of the public good to player 1, because if this player 2 is not contributing at all, then player 1 is there alone to contribute. So, that is the worth. Then we are getting this V1 dashed as a measure or as an indication of how much player 1 values that public good. If he values the public good less, he would be contributing less. If he values the public good more, he would have contributed more than V1 dashed. Sorry, V1 dashed inverse. Oh, sorry, 1 minute. Must have made some mistake. This should be inverse. So, V1 dashed inverse of 1, that is the worth of public good for player 1. So, how does it look in the diagram? Suppose this is C1 and this is C2, these are the two axes, and how to represent this equation 1? If C2 is 0, C1 is V1 dashed inverse of 1, C2 is 0, this is V1 dashed inverse of 1, and if C1 is 0, then C2 is of the same value, V1 dashed inverse of 1. And so, we have a downward sloping line representing the inverse relationship, and if C2 exceeds V1 dashed inverse, then C1 is 0, which means this best response function is this thick line. It coincides with the vertical axis above V1 dashed inverse of 1, and then it coincides with this downward sloping line and it stops here. So, this is my B1 C2. And similarly, I have to find out the best response function of player 2, which I can find by maximizing U2, which is a function of C1 and C2 with respect to C2, and we shall find the same kind of best response function, which is C2 will be a function of C1 now. It will be V2 dashed inverse of 1 minus C1. So, this will be my 2. So, this is best response function of player 1, player 2. Now, how to represent this? Now, to represent this, I have to have some idea whether V2 dash inverse of 1 is it higher or lower than V2 dash inverse of V1 dash inverse of 1. Suppose it is the case that this is higher than this. So, V2 dash inverse of 1 is higher than V1 dash inverse of 1. In that case, suppose this is V2 dashed inverse of 1. And this is again V2 dashed inverse of 1. Then how does this B2 look like? B2 as a function of C1. Here in B2 C1, C1 is the independent variable. So, for each value of C1 I have to find out what is the value of C2 which maximizes player 2's payoff, and this is given by this line. I am thickening it, and this part of the horizontal axis also, because if C1 exceeds this value V2, then C2 can take the minimum value of 0. So, we are getting this horizontal portion, and then this downward sloping part, So, this is my B2 C1. So, I have constructed the two best response function, one for player 1 and one for player 2, and from the diagram it is very clear that there is one and only one equilibrium, only one Nash equilibrium which is at 0 and V2 dashed inverse of 1. This is the only equilibrium that we can get. And what does it mean? That player 1 does not contribute. The C1 is equal to 0 and C2 is equal to V2 dashed inverse of 1. But this result that player 1 is not contributing at all and player 2 is contributing the entire thing is crucially dependent on these assumptions. That V2 dashed inverse of 1 is greater than V1 dashed inverse of 1. If it had been the other way around, then you can draw a diagram and see that then in that case it will be player 1 who will contribute the entire amount and player 2 will not contribute anything. So, and why is this happening? This is happening precisely because if we take this case, that is V2 dashed inverse of 1 greater than V1 dashed inverse of 1, that means the worth of the public good to player 2 is more than the worth of the public good to player 1. If you remember, we have just a couple of minutes ago we have shown that V1 dashed inverse of 1 is the worth of the public good to player 1. Similarly, we can show that V2 dashed inverse of 1 will be the worth of the public good to player 2. So, if the worth is more for player 2, this model is telling us that it will be player 2 who will contribute the entire amount, and the person who does not value that public good that much will not contribute anything, he will contribute 0. However, these two cases, that is, one is V2 dashed inverse of 1 greater than V1 dashed inverse of 1 and the other way, that is V1 dashed inverse of 1 greater than V2 dashed inverse of 1, do not exhaust all the possibilities, because we might have, instead of greater than, we may have this case also. This is also possible. In that case, there will be infinite number of equilibria, infinite number of Nash equilibria will be there, because what will happen then, that the two lines will coincide, two best response functions will coincide on this portion, on this downward sloping portion, and there are infinite number of such points here. So, all of them are Nash equilibria. So, here we are having situations where both of them are contributing, both the players are contributing for the public good. But obviously, this is sheerly a coincidence that my worth for the public good is same as your worth for the public good. So, in exceptional situations only, both the players will contribute, or both the players may contribute. Why I am saying this? Because in this case also there might be equilibrium here at this corner point where only one player is contributing. But of course, here there is a possibility that both the players will contribute. This was one application of best response functions for public good games. Let us now introduce some new concepts or new ideas in game theory which are widely used. this is the idea of dominated actions. To explain the idea, let me give you an illustration what it means. First, we shall talk about strict dominance. Okay. The idea is the following. Let us suppose that there is a road and on the road there is an intersection. To make it simple, let us say that this is a T intersection. So, the road looks like this, and it is, suppose it is a 2-lane road. So, there are 2 lanes in this road, and suppose in this intersection there is a red light obviously, and a car from here is coming and approaching to the intersection. And in the intersection right now there is a red light, and since there is a red light, one car is waiting here, waiting for the green light to come on. Now, for this car, it can choose to either go and wait behind this car here, or it can go this way and wait here. So, there are 2 actions here. What are the preferences? Any car does not like to be behind another car, because if you are behind another car, it restricts your movement. So, ideally I like to have no car in front of me, and it so happens that if this car which is waiting here at the intersection, let us call this the first car and this is the second car. If there is green light, then this car can go either this way, that is, it takes a turn to the left, or it can decide to move ahead. So, as player 2 has 2 actions, either to wait here or to wait here, player 1 also has 2 actions. It can either turn to the left or go straight ahead. However, if it decides to turn to the left, it will have to wait for some time, because there is a pedestrian here who is going to cross the road. So, since this pedestrian is going to cross this road, this car, if it decides to turn to the left, will have to wait for some time, which means the player 2, that is car 2, if it decides to wait behind the first car, it will also have to wait there when the green light comes. Now, here waiting on this lane, that is on the right lane, is better in any case, irrespective of the action of player 1, than waiting behind player 1, because if player 1 decides to go straight ahead, the first car decides to go straight ahead, what are the payoffs? If player 2 was behind player 1, it still remains behind player 1, which is worse than waiting here, because on the right lane, because if it had waited on the right lane, there would not have been any car in front of it. So, in this case player 2 is better off parking his car on the right lane. On the other hand, if player 1 decides to take the left turn, player 2 is definitely better off waiting on the right lane, because if player 1 decides to turn to the right, then it will have to wait, and which will make player 2 also wait here, because it is behind player 1. So, it means that no matter what player 1 does, player 2 is worse off by waiting behind player 1 instead of pulling up on this right lane. So, pulling up on the right lane will be strictly dominating the action of pulling up behind player 1. So, we call this strict domination, and the idea is that no matter what the other player does, one action is better than the other action, and the action which is better will be called a strictly dominating action, and the action which is worse will be called a strictly dominated action. So, let me give it a formal definition. So, for player I, action AI dashed strictly dominates action AI double dashed if both this AI dashed and AI double dashed are her actions, player I's action. If so this is the definition, that if there is one action AI dashed and another action AI double dashed, and if it so happens that no matter what the other players are doing, here this is coming for every possible list A not I of other players' action. So, I consider every possible set of actions or vector of actions by other players, and for each possible vector of actions of other player, it is so that by taking the action AI dashed, I get better payoff than taking the action AI double dashed. In that case, I call AI dashed strictly dominating over AI double dashed. Let me show this in terms of a payoff matrix so that it becomes more clear. Let us consider the following payoff matrix. Suppose this is player 2 and this is player 1, left and right, top, middle, bottom, and the payoff numbers are following. Now, let us look at this game from the point of view of player 1. From the point of view of player 1, I can see that no matter whether player 2 takes the action L or takes the action R, M is always better than T, because if player 2 takes the action L, M is better than T because 2 is greater than 1. If player 2 takes the action R, 1 is greater than 0, that is why M is again better than T. So, I say that M for player 1 strictly dominates T. However, it is also clear from this that if there are any two actions, it is not necessary that one strictly dominates over the other. Take the case of M and B. If player 2 takes the action L, M is better than B because 2 is greater than 1. If player 2 takes the action R, B is better than M because 3 is greater than 1. So, it is not necessary that strictly dominated actions or strictly dominating actions will exist. For example, if you remember the games that we have discussed before, Take the case of battle of sexes. In battle of sexes, there is no strictly dominated action. This was the structure. Here there is no strictly dominating or strictly dominated action, because if player 2 plays B, for player 1 it is better to play B. But if player 2 plays O, B no longer remains the best action, it now becomes O. But if you remember the prisoner's dilemma game, there were strictly dominating and strictly dominated actions. So, this is prisoner's dilemma. So, this was the game. Here if player 2 plays NC, then it is better for player 1 to play C. If player 2 plays C, again it is better for player 1 to play C. So, does not matter what player 2 does, it is best for him to play C. And similar logic applies for player 2 also. Does not matter what player 1 does, it is best for player 2 to play C. If he plays something else, he gets strictly less than what he is getting at C. And this illustration of prisoner's dilemma should give us an inkling that if we have a Nash equilibrium, then in that Nash equilibrium, strictly dominated actions are never going to be played, because in this prisoner's dilemma we have found that C and C both are strictly dominating actions, and NC and C are strictly dominated actions, and these NC and C strictly dominated actions are not being played in the Nash equilibrium, because in the Nash equilibrium only C and C are being played. So, let me write it down. In Nash equilibrium, strictly dominated actions and the logic is very simple. I can prove it in 2-3 steps. Firstly, what happens in Nash equilibrium? A is Nash equilibrium if for each I must have this ui this must happen in Nash equilibrium. Let us call this condition A. Now, suppose there is an action AI dash double dashed which is strictly dominated, and suppose it is being played in Nash equilibrium, then there is a contradiction, and we shall see that there is a contradiction. Suppose AI double dash is played, then what does I get? Player I get, he gets keeping the actions of other players constant. So, he gets this much. Now, if this is what he gets, now suppose he now switches over to AI dashed, that is the dominating action. Now, I know that this must be true by the definition of dominating action, which means that this condition is going to be violated if I consider that A I double dash is equal to A I star. So, if I instead of A I star I put A I double dash, then this condition A is going to be violated, which means that I am never going to be playing the strictly dominated action in Nash equilibrium, because I can from that action I can always deviate to A I dashed, and that will improve my payoff. Because if you remember, in strictly dominated action, for every possible list of action, it is better to play the strictly dominating action. So, this must be true for the star actions as well, and hence the A I double dash is not going to be played in Nash equilibrium. Let me now come to the other concept of domination, which is called weakly domination. And to motivate the idea, let me go back to that example of cars and intersection. So, once again we have this traffic intersection, and there is a car waiting here at the red light, car 1, and here car 2 is coming. It can either park its car here or it can pull up here. These are the two actions. Where should it go? Now, in case of weakly dominated action, if I have to show the example, suppose here in this case there is another car waiting here. Let us call it car number 3. Now, if there is a car number 3 waiting on the right lane as well, and there is a car 1 which is waiting at the left lane, both are waiting for at the traffic intersection because there is a red light. Then which is the better action for player 2? Here it is not very clear whether one is definitely better than the other, because it can so happen that player or the car number 1 also goes straight ahead and car number 3 also goes straight ahead. In that case, player 2 is indifferent. He can pull up either behind car number 1 or behind car number 3, it is all the same. However, it may so happen that player 1, that is car number 1, turns to the left, and like before there is a pedestrian here who is going to cross the road, in which case this car 1 will have to wait for some time and wait for this pedestrian to cross, and only then it will go to the left, which means there is a loss of time for car number 2, which means that depending on the actions of other players, one action can be strictly better, and there might be cases where both these actions are same for player 2, they are giving him the same payoff. In this case, we say that this action of going and pulling up behind car number 3 is weakly dominating the action of waiting behind player 1, that is car number 1. So, weakly dominating is a situation where it may happen that for some action of other players, these two actions are giving me the same payoff, which is the case when both this car 1 and 3 are going straight ahead. In that case, player 2 is indifferent. But there is one case, at least one case, where pulling up behind car number 3 is better. That is the case where player 1 decides to turn to the left. One important thing is that there is no indicator for player 1, I mean there is no indicator for player 1's car. So, player 2 cannot make out beforehand whether car number 1 is going to go straight ahead or going to turn to the left. So, if I have to formalize this, it will look like the following, that for player I A dashed action AI dash weakly dominates action AI double dashed if so for every possible action profile of other players, it must be the case that the weakly dominating action is giving player I at least same or more than the payoff he is getting from the weakly dominated action. But there is more, and at least one action profile this, which means that there must be at least one action profile by the other players coming from the other players such that the weakly dominating action, that is AI dashed, should be giving player I strictly more payoff than the action profile of AI double dashed, that is the weakly dominated action. So, this second thing is also important. Examples. Let me give you one example. Take the case of so here, to save space, save effort and time, let me write down the payoffs of player 1 only. So, these numbers 1, 0, 2, 0, 2, 1 are just payoffs which player 1 gets, not player 2's payoffs. Now, suppose I have to compare between T and M. Now, I can see that if player 2 plays R, player 1 is indifferent between T and M. However, if player 2 plays L, then M is better than T. So, here I have this satisfaction of weakly dominating and dominated actions, and I say that M weakly dominates T, because M is better than T if L is played. M is giving the player 1 same amount as T is giving if R is played. What about M and B? Again I see that B weakly dominates M, because if L is played, M and B are same, they are giving player 1 same payoff. If R is played, B is giving player 1 better payoff. So, this is weakly dominating and weakly dominated actions. Are weakly dominated actions played in Nash equilibrium? Well, there are two results here. One is that in strict Nash equilibrium, weakly dominated actions are not played. And how do I know that? If you remember what was strict Nash equilibrium, strict Nash equilibrium was such that suppose A star is strictly Nash equilibrium. If for all I what must happen is that ui A star is strictly greater than this was the definition of strict Nash equilibrium, that for each player, if he plays something else, if he plays some other action other than the Nash equilibrium action, his payoff should go down. Now, from this one can conclude that in strict Nash equilibrium, weakly dominated actions are not going to be played, because if you are playing weakly dominated actions, suppose you are some player I is playing a weakly dominated action AI double dashed, then there must be some action which is weakly dominating this action, which is AI dashed. Now, if player I changes his action from AI double dash to AI dash, then how is his payoff going to be affected? Either it is going to remain constant depending on the action profile of other players, or it will go up, because AI dashed is strictly dominating AI double dashed. So, if he shifts from the double dash to the dashed, it can either go up or it will remain constant. But whatever it is not going to satisfy this condition, because this condition demands that if you shift, then your payoff must go down. Here it is remaining constant or going up. So, any action which is weakly dominated is never going to be played in strict Nash equilibrium. Can weakly dominated actions be played in non-strict Nash equilibrium? And the answer is yes. So, weakly dominated actions can be played in non-strict Nash equilibrium. And the idea is not very difficult to grasp. In non-strict Nash equilibrium, if people deviate, there is unilateral deviation of their actions, it may happen that their payoff is remaining constant. Only thing we need is that it should not go up. So, it can go down or it may remain constant in non-strict Nash equilibrium. Now, in weakly dominated actions also, if you shift to a weakly dominating action from the weakly dominated action, the payoff not necessarily goes up, it may also remain constant. So, there is a bit of consistency between weakly dominated actions and a Nash equilibrium action in a non-strict Nash equilibrium. So, that is why it can be possible that a weakly dominated action is being played in non-strict Nash equilibrium. I shall give you one example where it happens. So, this is the example, this is a payoff matrix. There are 2 players and 2 actions for each player. Now, which is the dominating, weakly dominating action here? I can see clearly that for player 1, for example, B is weakly dominating C, because if player 2 plays B, it is better to play B. If player 2 plays C, player 1 is indifferent between B and C, so which means the B is weakly dominating C. And the same thing will happen for player 2 also. For player 2 also, B is weakly dominating C, because if player 1 is playing B, then it is better for player 2 to play B. If player 1 is playing C, player 2 is indifferent. So, for player 2 also, B is weakly dominating C. However, what are the Nash equilibria in this game? There are 2 Nash equilibria, one is BB and the other is CC. You can check it out that if the other player is playing B, no player is going to shift from B, because that is going to reduce the payoff. What about CC? Well, if the other player is playing C and if you deviate, then your payoff is not going to go down, it is going to remain constant, but that is included in the definition of Nash equilibrium. It may happen that you deviate and your payoff remains constant, so that does not invalidate the Nash equilibrium. So, CC is an equilibrium where you have dominated, that is weakly dominated, actions are being played. So, these are some of the properties of strict Nash equilibrium and its relationship with weakly dominated or strongly dominated actions. Before we end this lecture here, let me just recapitulate what we have discussed in this lecture. We have discussed the game of public goods, where people can take infinite number of actions. People can decide to contribute more towards the public good or less, and we have found out what is the Nash equilibrium in that case, depending on a certain particular payoff function. And we have seen that in the equilibrium, in most of the cases there will be a single Nash equilibrium. In that Nash equilibrium, a single player will contribute the entire amount, the other player will not contribute at all. In a sheer case of coincidence, it may happen there are infinite number of Nash equilibria, in which case both the players contribute. That is what we have done, and then we have introduced the concept of dominating actions. We have talked about dominating actions, strict dominance and weak dominance, and what is the relationship between this dominated actions and strict Nash equilibrium. We have seen that in strict Nash equilibrium, strictly dominated actions are not played. In non-strict Nash equilibrium, weakly dominated actions might be played, and in Nash equilibrium in general, strictly dominated actions are not played. Thank you. Two people are to divide 10 rupees between them. Each calls a whole number between 0 and 10. If the sum of the numbers is at most 10, they get the money equal to the numbers they called. If the sum is more than 10, firstly, player calling the lower number gets the same amount of the money, other player gets the balance if the numbers are different. Each gets 5 if the numbers are same. Find the equilibrium or equilibria of the game. So, this question basically asks us to use the idea of best response functions to find out the equilibrium or equilibria of the game. So, let us try to find out how the best response function of player I looks like. I could be 1 or 2. So, suppose the other player is calling 0. What should be the best response for this player? I claim that the best response should be to call 10. I could be 1, I could be 2. Why? Because if suppose I am player 1, if player 2 has called 0, then if I call 10, I get 10. There cannot be anything more than this. This is the maximum that I can get. So, now if for example the other player is calling 1, then what is my best response? Here if the other player is calling 1, I should call either 9 or 10. Both are my best responses. In either case, what I am getting is 9. Similarly, if the other player is calling 2, the maximum that I can get is 8, which I will get if I call 8. If I call 9, again I will get 8. If I call 10 also, I will get 8, because in these last two cases the sum is exceeding 10, and if the sum is exceeding 10, the rule is that the lower number, the person who is calling the lower number will get the money, that is the other player will get 2 rupees, I will get the rest, which is 8. So, likewise it will go on. If the other player is calling 3, I should call 7 or 8 or 9 or 10. In either case I am getting 7 rupees. So, this way it will go on. If for example the other player is calling 5, let us write it for 4. For 4, these are the best responses. If the other player is calling 5, I can call 5, because here the maximum I can expect to get is 5. If I call more than 5, it does not matter, I get 5 rupees. Now, suppose the other player is calling 6. In this case, however, this kind of rule that we were following will not hold. If the other player is calling 6, the maximum that I can expect to get is 5 rupees, which will happen if I call 5, I will get 5, or if I call 6, then the numbers are equal. So, we shall divide this 10 rupees, which means I will get 5 rupees. If the other guy is calling 7, I will undercut him, I will call 6 and I will get 6. So, here it will be 7, then 8 and 9. Now, these best responses are true for each of these two players. I could be 1, I could be 2, and looking at these best responses, it is found that there are only 4 Nash equilibria. Which are these 4? Such that the best responses are matching with each other. These are 5, 5. Why 5, 5? Because if the first player is getting the call, is calling 5, the second player will call 5, and if the first player if the second player calls 5, the first player will again call 5, because I could be 1, I could be 2. Similarly, 6, 6 is also a Nash equilibrium, because you can see 6 is the best response to 6 for each of these two players. In these two cases, there are 2 Nash equilibria, but I also claim that these two are also Nash equilibrium, that if 5 is called, 6 is the best response.
If 6 is called, 5 is the best response. So, this is Nash equilibrium. For the same reason, this is a Nash equilibrium. Thank you.